Now, rocks have given us glass, which is considered perhaps the most important discovery in science, the microscope for biology and the telescope for physics and analyzing the gases with glassware in chemistry. But it might also give us the second most important discovery in biology as well. So it's called fluorescence. So it's technically a mineral, not a rock, and it was studied and named as fluorescence by looking at the mineral fluorite, which you see here, by Sir George Stokes, 1852. And so I'll get to why that's the second most important discovery in biology in a second. We'll just have a look at it first. So what's really unusual about this is the UV wavelength is absorbed, but not UV wavelength emitted. So with visible light, it's usually directly related. Whatever's absorbed is emitted. And so with fluorite, you see the UV wavelength is absorbed, but a slightly less energetic wavelength is emitted. So you can see the blue visible light here being emitted by the fluorite. And so some of the energy has actually been lost and a less energetic wavelength has been released, which is not what you see with all the colors, right? It's usually the exact amount of energy that the electron has moved up for that wavelength is the one that's absorbed. And so you'll see the opposing color based on the color wheel, okay? Because that's how your eyes interpret color. All right, so I've got all these well-known examples here of fluorescence, but nothing's nowhere near as good as the fluorite. The fluorites are really, really good. The opal and chalcedony in the agate did give a few specks, but the camera didn't pick it up. And all the others I'm showing you, but the calcite didn't work at all, which I'll explain later. Okay, so the fluorite should be clear because there's not enough energy for the light waves to excite the electron up. The distance between in the valence shells is too large, and so it should just go straight through and be clear. That's technically called electronic band theory if you want to follow that up a bit more. There is a green tint that comes from the metal impurities, and so the reason why UV light interacts with this is something called an F center. There's actually calcium ions missing and just electrons. And so the UV light gets caught up in that and interacts with that and loses some energy. And so these they interact with it, and then it loses some energy and gives off a lesser wavelength. So some sources say it's heat that's being lost. And also note these impurities or defects are in the levels of parts per million. They're very, very small. And so sodalite here gives off some, it's blue and it gives off some green specks. They look quite nice, but the camera doesn't pick it up that well actually. And the oyster shell contains calcite and aragonite. It's giving the green edges, just like the aragonite crystal, which is normally red due to the iron impurities. And it's showing a really nice green, which is a real decrease in energy. And so my very clean crystal calcite comes up empty because the theories are that the reason there is fluorescence is because the electrons get caught up in the wrong places and then have trouble finding their way down and lose energy in that. And so the defects or impurities cause a loss of energy, and so you can see a lesser wavelength released. And that the more defects and impurities in the crystal, the better the fluorescence. And so having a super clean calcite sample was not the best choice and the only one that didn't actually work. And I also tried to get phosphorescence, which is if you really excite the electrons and sometimes can reverse their spin, and then it takes even longer for them to get back to the right spin to go back down to the ground state. But I didn't get that to work. I don't know if that was lack of patience for me. I should have left it longer, or I needed a stronger UV light or something, or a less pure sample. Okay, so I'm going to put this one out here as the really big one for biology because I often a little bit critical of the way biology is taught because it's not based on experimental evidence. And this is how they know. All right, so they've found molecules that they can actually attach fluorescent molecules. They're called green fluorescent proteins, and they can actually attach a fluorescent molecule to other molecules and then track them with a microscope. So they know exactly where the molecules come from, what they're doing, where they're going. All right. And so this is why I'm saying this is the second most important after the microscope. This is the second most important key experimental evidence in biology, and it's all thanks to rocks, as they all seem to be.